Hey there, everybody. Welcome back. We're going to do another example of LaGrange multipliers. I don't think I have that here, and we're doing LaGrange multipliers. And so we've got a word problem. A shipping company handles rectangular boxes, provided that the sum of the dimensions of the box, length, width, and height, are 96 inches or less. Find the dimensions that yield the maximum volume. So what we need to do is go ahead and give this a try before we talk about it, though. We are looking at volume, and we have some constraint function where the sum of the dimensions are 96 or less. I'm going to assume the volume is biggest when the sum is at 96. And so you're looking for a gradient of f equals lambda times the gradient of g, where g is the constraining function. That would be the sum. So the sum will be our constraint, and the max volume will be our function that we're trying to maximize. Go ahead and pause it and try to work it out. I'll assume you did. I didn't use L, W, and H. I used X, Y, and Z for my length, width, and height. So my volume is going to be the product of those three, X, Y, Z. And we're constraining it so that the sum of those dimensions are less than 96. X plus Y plus Z equals 96, less than or equal to 96. I'm going to assume it's maximized at 96. So if I solve that, set equal to 0, that will give me my G. So my V function is my F. This is my function to be maximized. My constraining function is the dimension sums. Let's work through it. If I take the gradient of F, or gradient, I'll use V. I think I use V throughout this. Gradient V is YZ, XZ, and XY. If we do lambda times the gradient of G, we've got lambda times 1, 1, 1. So we're going to set those equal to each other. And I get three equations. YZ equals lambda, X equals lambda, and XY equals lambda. Which means these should all equal each other. Since they all equal lambda, they all equal each other. So let's just start pairing them up. I'll pair up A and B first. If I pair up A and B, I've got YZ equals XZ. And we know, well, Z could be 0. I'm going to assume it's not. And we've got Y equals X. Either way, we have Y equals X. So that's good. And then let's pair up another two. Let's pair up B and C. If we pair up B and Z, we've got XZ equals XY. So we can show that Z equals Y from that. And so we had X equals Y and Y equals Z. So all three have to equal each other. So we're going to plug this into our constraint function to find out what X, Y, and Z are. Once we find out what X, Y, and Z are, we can plug them into our volume function to figure out actually what that max volume is. It said to find the dimensions for it, but let's find the max volume as well. So I've got X, Y, and Z equal each other. We plug it in. I'm going to use Z for all of them. So X plus Y plus Z becomes Z plus Z plus Z. We've got 3Z minus 96 equals 0, or Z equals 32, which means they all equal 32. And so my volume function is 32 times 32 times 32. This was measured in inches. So I've got 32 cubic inches, which is 32,768 cubic inches. So the volume function, it has no limits. I mean, we can do all of X, Y, Z to do the volume function. So that's where the beauty of this works out. Volume is an infinite function. We can plug in any of the values. Although negative values don't make sense. So maybe we're focusing in the first octant. But we've got some constraining function in that first octant where we want those the sum of the variables to equal 96. And so there we go. The next video is a little bit longer, but it'll be our last for LaGrange multipliers. Peace.